All right. But good news. I don't have to tell you all the joke of the day today. So, here, Leo will search for the joke. I'll give you all some context. I got the line and stuff like that. Ooh, nice chicken. I didn't see the chicken head. I guess this is probably the best pictures I have here currently. So that's my daughter. Dressed up as a lion. She chose a lot. She just likes animals. So what goes with being a lion? So it's Daniel and the lion's den, and there you go. So there's the context, though. If you're like, why is he dressed up that way? My daughter likes animals, and there's my wife, and our 4-month-old who's also a lion. Everyone's a lion. But there you go. There's a little slice of life. All right, Leo, go for it.
Okay. I have, why do bees have sticky hair? Because they use honeycomb.
Ready, go. Come on, Leo.
I don't remember that at all.
Come on. Wow. Nothing worse than a comedian that tells a joke.
Did we get this one? At a zoo, there was a baguette in a cage. It was bred in captivity.
There you go. You redeemed yourself. All right, so last class we talked about universal gravity, and I tried to convey the wonder of how Isaac Newton discovered this. We did some problems with it, so let's just jump to the equation. Boom, there it is. So Isaac Newton discovered this. On Earth, he could do measurements with force and find that if you have 3 times the mass, it's 3 times the force, so he could figure out the mass was on top. And then the r squared on bottom, and I don't think I did a fantastic job of conveying this. So, there was also the acceleration equation. Boom, there's that. So all Isaac Newton had to do, and I say all he had to do was take the ratio that the moon experiences, the ratio of the acceleration to the moon, and the acceleration that we experience on Earth, and then he set that equal to this expression. He didn't know what this r to the n was yet. He didn't know if it was a power or not. So you got mass of moon, or no, this is mass of Earth over r. This is moon, this is Earth. The g cancels, the mass of the Earth cancels, and you get, if you can find the acceleration on the moon, he can find this ratio. And how did he do that? A equals b squared over r. Where r is how far away the moon. Whatever. You don't need to know this, but it's cool. I conveyed some of that. I did an okay job. Probably not as good as I could have. So cool. People are, like, if you ever look in the past, so this was 400 years ago. 400 years ago is when he did this, which is just like the U.S. didn't exist then, right? 16 something, like late 1600s. The U.S. The U.S. wasn't even a thing yet. Like, before the U.S. was even a thing, this was figured out, which is just like, it's wild, y'all. You all can do cool stuff, but you got to be clever. You got to be really, really, really clever. And then my friend I was chatting with, he's visiting. He also raised a good point. Not only do you need to be clever, you need to be observant. You need to be like not neglecting things. So, for example, argon was discovered by a 0.7% error. Like, that's how they discovered argon, and that's a very small error, and most people will just chalk that up to randomness. But the element argon was discovered because people were observing and was like, these are different by 0.7%. Maybe there's a reason why. And they did a bunch of things and whatever. So there you go. Figured out the velocity of the moon. Cool stuff. All right. I forgot I already said this a bunch of times. But let's see if it's settled. So yeah. Just know that if someone gives you a task that seems impossible, it might be impossible. But if you're clever enough, you might find a solution. And if you do, you'll get paid a lot of money. Probably. I was like, those are the people that get paid a lot. The people that find solutions to things that seem impossible. Those are the people that do great things. All right, so what approximate path does the moon take when it orbits the Earth? circle, square, octagon, tetrahedron.
Don't get it wrong, please.
Yeah. Yeah, if y'all get this wrong. Thanks. Yeah. Okay. You should be able to do it on a laptop. Yeah. If you log into iClicker on there, and I'll wait a second, you should be able to respond to it on any electronic device. Because I've seen some people doing it on their laptops. That's the only reason I say that.
Yeah, some people do full use here.
Oh yeah. I have I might switch to Top Hat for the spring. They came and advertised to me. We'll see.
Yeah, I still have to figure out what class I'm doing because if I don't end up taking mechanics,
just remind me and I'll give you the points for it later. Don't worry about it. All right. So what's the path? Did we all get it right? Oh my gosh. Wow. I think one person did it out of principle. Okay. Look, you all know, except for one person. Normally I don't. It's a circle. Wow. Roughly. It's approximately a circle. Pretty much all major planetary bodies, there's something called eccentricity, and it describes how circular that orbit is. The closer to one it is, the more circular it is. Pretty much all of them. Let's just look it up. Let's just look up the eccentricity of the moon. Eccentricity of the moon. Oh, sorry, I went the wrong way. I said closer to 1 is more circular. I guess it's closer to 0 is more circular. Shows what I know. Not much.
Look up Mercury's.
All right, so 0.0549, which is actually closer than I thought. Eccentricity of Mercury.
That's the most exact one.
Ooh, look at that one. 0.21. So, because Leo actually knows more space things than me, this is the least circular orbit. You could maybe, fun thing. Why is it so high?
We can predict accurately Mercury's orbit until we knew about general relativity.
Ooh, say it on the mic. He's got fun fact for you. So, circular is really simple, right? It's a nice circle. You'll have equations for it.
Is it general or special? I think it's general. Yeah.
Special is. Oh no. General.
Yeah. Yeah. So we couldn't accurately predict Mercury's orbit. It was off by it would precess once every 100 years that we couldn't account for with Newtonian mechanics until Einstein came along and provided general relativity. Because Mercury is so close to the gravitational field of the sun that its orbit precesses when an accountant can't calculate with Newtonian mechanics.
So if y'all watched Interstellar, gravitational stuff does weird things.
Black hole stuff.
Yeah. So yeah, cool stuff, y'all. Physics. Things get we're doing the simplest cases. I was talking to a student recently. He's actually in this class. I won't call him out because I don't want to embarrass him. I highly encourage every single one of you get involved in some club or project where you're actually doing the things that you want to be doing in the future, because you're going to realize it's one thing to learn how to do something. So I'm giving you all the basics, but man, when you start actually trying to make a product, whether that's a code, a software, or whether that's a rocket, or whether that's like a car, man, you'd be shocked at the things that come up that you wouldn't even expect that you have to account for. Engineering, the challenge is in the details. I'm giving you all the foundation, but man, when you actually do real world stuff, you have to account for stuff that I haven't taught you. And you're only going to learn about those things doing a project. That is the reality. If you don't believe me, you'll find that out one day. Highly, highly, highly encourage you all, get involved in some club or some project. You can just do it on your own, but I will say if you join a group of people, you can do something even cooler. And also you're going to learn what it looks like to work with a group of people, and that's its own group of challenges. The person I was talking to was talking about change logs. So if someone in you break a team into a bunch of teams, if they make a change, they have to communicate that change. And how do you do that effectively so that everyone's working together towards the same goal and has all the information logistics, change logs, all these kind of things. Do it sooner than later, because that's what's going to make you stand out. That's what's going to make you actually marketable. That's when you apply for an internship or things like that. Everyone's taking the classes and getting the grades. Yes, sure, there's a baseline for that. But what's going to make you distinct is if you actually put yourself out there and you actually I've already done engineering project. I've already written software that accomplishes some goal, not because I had to, but because I enjoy doing it, and that's what sets you apart. Anyway, whatever. That's my professional spiel. All right, great. Things that go in a circle. Centripetal force, mv squared over r. Remember that the centripetal force is if you add up all the forces pointed inwards or outwards, it equals the centripetal force, and they're actually very fortunate in space. We only have to account for gravity. There's no air resistance. We don't need to worry about the... there is a slight force due to the radiation emitted from the sun. That's for solar sails, but it's like negligible. Yeah, there's radiation pressure, which is a weird thing. Which is what else? Yeah, that's the correct term for it. So anyway, in space, all you gotta worry about is gravity. There's the equation for it. Now, we can only use this equation if we assume a perfectly circular orbit. There's always the phrase, you know what you say about people that assume. And my follow-up to that is it makes you a really good physicist. Physicists always make assumptions. So that's, assume it's a spherical cow. Like, that's always the joke, right? Yeah, it's just one of the things you got to do to actually get very far in calculations. Now, again, if you're in engineering, you unfortunately will have to account for all the things. More things than us physicists do. So have fun with that. But if y'all notice, there's some cool stuff that happens with this equation. Yeah, look, mass 1 cancels out. So to clarify here, mass 1 is the object going in the circle. So you got your planet. That's mass 2, or it doesn't need to be a planet, but whatever. Then you have your thing that's orbiting the planet. That's the one actually traveling in a circle. Technically, they're both orbiting the center of mass, but we're not going to worry about that right now. The velocity is the velocity of the one that's going in the circle. And the radius here, and this is important, it's a very subtle thing, but it can make a big difference. The radius is not the distance from the surface to the surface. The radius is that this r is the distance from the middle of the center of masses. So it's the distance between the two centers of the objects, generally. So that can matter because if you have a satellite orbiting the Earth, you're not going to use the distance from the surface of the Earth to the orbit. You're going to use the distance from the center of the Earth to it. But let's cancel even more things. One of the r's cancels here. That r cancels there. And long story short, we'll do some calculations with this. If you want to find the mass of a planet, like you want to find the mass of the Earth, all you need to know is the gravitational constant and how fast the moon is going around it, which is like super cool. You want to, that's all you need to find the mass of the Earth, is how fast the moon is going and the value of g. So you can find, this is how they find the mass of planets, y'all. They look at something orbiting that planet, they measure how fast it's going, and they square it and divide it by g. And today you have the mass of any planet you want, which is like wild that you can find the mass of a planet by this. Like, so simple. That's what makes it so cool.
Well, for this, the Earth is... Would it be still if you find it? Like the Earth's velocity?
We could do it ourselves. Yeah.
If you...
Not the Earth's velocity, the moon's velocity.
I think maybe you could because the Earth rotates around a very center with the moon.
Oh, yeah. We would approximate that the Earth was stationary. So, yeah, we can do this with Jupiter. Find the mass of Jupiter. You don't care that Jupiter is made of gas. You don't care how far away Io is. You don't care anything about, you don't care that Jupiter's spinning. All you care about is that its moon has is this far away. Okay, in this case, I gave you the radius because I'm going to have you do a couple things. I actually do give you the radius here, but you wouldn't need that. You would just need to know how fast it's going and the gravitational constant. Now, the values I gave you, you're going to need to figure out how fast it's going. So I'm going to let you all try to struggle through that. Orbital radius of 421,700 kilometers in a period of 1.77 days. Period is the time it takes for one full revolution, one full orbit. And then after this one, we will find the mass of the Earth by figuring out how fast the moon's going. We'll just see how close we get. We'll see how accurate it is. Again, you all can measure how fast the moon's going. Just watch it go across the star, and distance divided by time. Oh, I'll put the answer up here. It's not going to spoil anything.
Jupiter.
Yeah. Do you have it memorized, Leo? Is it a test of how good of a space person you are?
Jupiter memorized.
Wow.
I know it's incredibly.
Jupiter is a big boy. Jupiter is 1,000 times bigger than the Earth. The Earth was to the 24, which might not seem that much bigger, but if you had an object that's 1,000 times bigger than you, it's a lot bigger than you.
I think Jupiter's only 100 times bigger than Earth.
Radius-wise?
Diameter is about 11 times that of Earth.
Yeah.
It's 1,000 times more massive.
Yeah, volume does. You cube it, makes sense. 11 times 11 times 11. Well, it wouldn't be 11, but whatever the radius is. Yeah. Well, the radius would be 11 times bigger too. So
yeah, the Earth is denser too, by a little bit.
That makes that tracks. Gaseous.
But Jupiter just has so much pressure that it has so much space and such a low volume.
Yeah.
It's hydrogen, it's like metallic.
It's I've heard the analogy. It's basically a baby star.
Yeah.
It's the star that tried so hard but couldn't make it. And again, I'll give you all a hint. I'll write the equation I put on the last slide. Yeah. In case you didn't write that down, that's going to be relevant. Any ideas, y'all?
Oh, wait, no, still the
Ooh, yeah, what uses the distance? So the distance won't be the radius, and that would mean that it's crashing into the dale. Or crashing into the you have the right idea. What is the path that this thing takes? It's not a straight line. It's got it. Wait, hold on. What's the path that Io takes? So what path? How do you find it? There you go. Yeah. All right, and while y'all are having so fun with this, you're having a great time. Don't lie to yourself. Boom, boom. Blinky, blinky. Oh, okay. Okay, how'd you get the velocity? What's the distance that you're traveling?
Okay. Write it that it isn't.
How are you all doing over here? Do you have an idea? Strat? So what do we, based on that equation, what will we need? We don't need the mass to actually cancel. Well, we're going to find that. That's what we're solving. Yeah, so we don't need to know the mass of Io, which is cool. We're solving for the mass of Jupiter. So that in that equation, what variables do you need? Velocity. So we have radius, so yep, we got that. We need the velocity. Yes, it will have a different acceleration due to gravity. We can do that. And the key here is what path is it taking? It's a circle. And so yeah, think about it. So we're gonna need to find velocity. So that's really the question. How do we find the velocity of this given the information I've given you? I've given you the time it takes for one full loop, and I've given you the radius of that circle.
This isn't working. Can I?
Yeah. Yeah. What's the distance it travels? Oh yeah, what's the word for that? The distance between diameter. No, it's not diameter. It's the circumference. Not pi squared. Yeah. So you got distance. You can find distance. And there's actually, if y'all remember, tangential velocity. It's actually in the formula sheet. V equals 2 pi r over time. It's somewhere in the formula sheet. Because you've derived the equation yourself again. Yep. All right. I'm going to get rid of the blinky blinky. Okay, so I did misspeak before. We did need the radius, actually. You do need to know how far away you are from the planet, but there's clever ways of doing that. Remember, they figured out how far away the moon was 400, actually more than 400 years ago. Like 600, I don't know, some crazy amount. All right, so if we simplify this equation, if we want to find the mass, we have v squared equals g m2 over r. So long story short, if we want to get the mass, we need the velocity, we need how far away it is, and we need the gravitational constant, which is just a number. So yeah, really the question is, great, let's write down our givens. We have R. That's like straight up given. 421, 700. And I'm just going to convert this to meters by chucking a times 10 to the 3 at the end of it. That's the easy way to avoid mistakes. And we have we have period. If you all remember way back, I told you all period is a time for one full cycle. Period is a time for one full cycle. And this is in days, which is gross. You immediately probably recognize we're going to need to convert that to what unit? Seconds. How do I do that? Multiply it by times 24. That's going to get me how many hours? Times 60. That's going to get me how many minutes? Times 60. Yeah, what's that? Sorry, what's the final result? 152,928. All right, great. Okay, so we got radius, we got the time. What are we solving for? We are solving for the mass of Jupiter. So yeah, now the question is, how do we find the velocity? Because that's the only thing we're missing. And to do that, we skipped a step that we should have done. Draw a picture. There's Jupiter. There's Io. And drawing this picture reminds us that Io is going in a circle. And there's lots of nice things about circles. Lots and lots of nice things. There's an equation in your formula sheet for the velocity. But what was cool is pretty much everyone I talked to, you all basically derived the expression yourself. Y'all tell me, how do I get the velocity? Okay, basic kinematics. Distance divided by time. Remember, y'all, velocity, if it's a constant, we can just do distance divided by time. And then you just ask yourself, what is the distance that this thing travels? What's the path it's taking? It's a circle. How do I find the distance in a single circle? 2 pi r divided by the time it takes for that one circle. So if you haven't done this calculation, there you go. Try it out. See if you can get the right answer. So yeah, all you need to find the mass of any planet is how fast an orbital something's going around it and how far away it is. And they actually did this with, I forget which planet. They sent a satellite around it, and it's like get really accurate values for the mass of various planets. You can also just look at the moons that orbit it and all that kind of jazz. A satellite will give you slightly more accurate measurements because a satellite's mass is really low. So when things orbit, they orbit around the combined center of mass of the system, which is a whole thing that we'll talk about. So technically, Io doesn't orbit around the center of Jupiter. It orbits around the center of mass of the two objects together. They orbit around a shared point, which is kind of wild. But if you have something really small, you can approximate that as 0. So, all right, so step 4, V equals 2 pi times 4.217 times 10 to the 1, 2, 3, 4, 5, 8. Divided by 1.52, 1.53 times 10 to the 5. I use scientific notation because I don't want to write I don't know if I save myself much writing, but I have a natural tendency to avoid writing big numbers. It just gets so hard to figure out what they are. Scientific notation is just a little cleaner in my mind. Makes my brain easier. Makes it easier for my brain to figure out things. All right. Shock and awe. It's going really fast. Everything in space goes really fast. There's no air to slow it down. So like you can get cooking. All right. And so then the mass equals neural. So mass 2 equals the velocity squared, which is that number 17,317.8 squared, times the radius, which is that 4.217 E8, divided by gravitational constant is 6.674 times 10 to the minus 11. I will give you that constant on the test, but you will end up memorizing it almost guaranteed if you just do enough of these problems. And then you'll forget it again when you stop using it and life goes on. Yeah. All right. And the mass of Jupiter is 1.89 times 10 to the 27 kilograms. Okay, and then we fact check ourselves. That is the answer that's on the thing. That's not surprising. If I just quickly do a Google search for mass of Jupiter, 1.89. How close were we? Oh, it's the same one. Now, granted, I don't know if these numbers were kind of cherry picked. So, to actually get a sense of how accurate this is with planetary bodies, let's find the mass of the Earth. So let's find the mass of the Earth as if we existed 300 years ago, where they knew the radius of how far away the moon was. They knew the velocity of the moon. And let's just do that calculation like they did 300 years ago and find the mass of the Earth. And then we'll compare it to the real value that we know nowadays. Now, some of this can be a little bit caveat. I don't know the numbers I'm going to get, so distance of moon from Earth, they did not have this value super accurate way back when. So we're going to take one that's very much rounded to approximate that. So the moon is, I'll just make that black font so you can actually read it. 384,000 kilometers away and travels at a velocity of moon 1.022 kilometers per second. I'm just going to take that fun unit. 1.022 kilometers per second. How much mass does Earth have? All right, try it out. Should be a pretty quick one because you don't have to find velocity. I give it to you. And we'll see. And again, the distance we're using here is far more accurate than they probably had 300 years ago or 400 years ago. The velocity, that one actually probably is, yeah, I don't know how accurate, how much error they had back then. So we're a little bit more blessed than they were, but this is basically all they had as well. They did need the gravitational constant, which they could only have gotten from Cavendish's experiments. So that was 300 years ago.
Yeah, sometimes what I do when like really big numbers like this, if everything is multiplied, you can just pull out the power of the ton. And do them separately, but sometimes it can confuse people.
Yeah.
But when you're like writing really long things, it can be helpful sometimes because you have everything just subtract the four.
Yeah, no, it is handy. I'll show it. I can show it in the math.
Yeah, but it can trip people up because sometimes they do like stuff like that and you can't.
So the radius of the moon is 3.844 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 meters. The velocity is going to be 1.022 times 10 to the 3 meters per second. We're solving for the mass of Earth equals question mark. mv squared over r equals... Oh, I also am not going to give you all this equation of mg squared over r equals the gravitational force in the formula sheet. I will give you the force of gravity. I will give you centripetal forces in... Actually, I don't even give you centripetal... Actually, let's just look at the formula sheet. You'll have to build this equation on the test. Because it's a circular motion problem. It's secretly a circular motion problem. So... what do I give you all in the test? I give you that the centripetal acceleration is v squared over r. I give you F equals ma. And where is it? And I give you this. So you have to actually build this equation on if you're actually solving this problem. You have to realize it's going in a circle. Things going in a circle is mv squared over r equals the sum of all forces pointed inwards and outwards. So I say that because when we're solving these problems today, don't take this for granted, this equation, this setup. You actually have to kind of, either you have it memorized, you can put it on your note card too if you're really worried about it, or you can derive it really simply. Whatever. There you go. Just, I wanted to point that out to you all though, so you weren't, you don't get too used to a good thing. All right. So boom, that goes away. Mass 1 goes away. So, you know, we rearrange this just like we did last time. The velocity, the mass equals the velocity squared times r divided by g. And we plug in the numbers. 1.022 E3 squared times 3.844 E8. Divided by 6.674 e to the minus 11. So when I get to this point, I just kind of chuck it all into the calculator. If you want, you can like cancel out some of the scientific notation. E8 on top, you'll subtract the E11 on the bottom, so that becomes e to the positive 19. And then E3 squared will be E6, and you add that to it, and so that is a way to kind of check your work in some ways, is to kind of check those notations. But you chuck this whole thing and you get 6.015 times 10 to the 24 kilograms. And this is making some significant assumptions, specifically that circular orbit. And if we look at the actual answer, mass of Earth, 5.97 times 10 to the 24 kilograms. Look how close we got. Like, that's not that far off. The actual answer, the real one is 5.97 times 10 to the 24. That's really close. And again, it's absolutely wild. You don't need to know the density of the Earth. You don't need to know that the Earth has various layers with crust and magma and all that nonsense. You don't care about like anything about the composition. You don't care that the Earth is slightly bulging in the middle because it's spinning and that centripetal force in the middle is you need more centripetal force. You don't care about any of that. All you care about is how fast the moon's going and how far away it is, and you can find the mass of the Earth. That's just like, I don't know. It's wild to me, at least, that you can do it so simply. And this is the power of cleverness and physics and all that kind of stuff. So, there you go, y'all. Good stuff. All right. Boom. Now, we're going to take this force equation and we're going to relate it to, we're going to find the energy, the gravitational energy equation, using the stuff we covered. So, that's what we're building towards. What is the relationship between potential energy and work? It's a little, okay. This was one of those relationships I gave you all a while back. Don't worry, I'm not going to test you on this. Oh, it broke? Oh, I think that it's just very upset right now. It's not unplugged because it's showing it. All right, we're just going to end this. We're just going to unplug this, replug this. Oh, iClicker just shut down entirely on its own accord. Gave up on life. Yeah. No, my costume. I'm Daniel in the Lion's Den. It's a biblical story thing. No. I'm Daniel in the Lions. So my daughter's dressed up as a lion. There's a biblical story of Daniel getting tossed into the den of lions, and the angel shuts the mouth of the lions.
I thought you were like a samurai.
So.
I guess
No, that's fine. That's why I got a little name tag that says Daniel. I do not assume everyone, and I don't even assume everyone knows this story. Look, my daughter dressed up as a lion, and so I had to figure out something that goes with a lion. And so a bed sheet with a hole cut in it was really easy. That's legitimately how we made this last night. We had an old bed sheet that was from the rags, and I cut a hole in it. And we had this random piece of cloth. So,
like a wizard.
Yeah, it's some fuzzy blanket. So it was a very, very easy costume thing. That was that tied in. So that was the inspiration there.
You have sandals on?
No, I did last night, but I was like, I don't want to be walking around in flip flops today. Last night I did, and tonight for Halloween I will. But I'm like, I like socks. I don't like sand in my feet. Seconds. I don't even think this one's on the formula sheet. Because to be honest, you're not really going to use this. So this equation, we're only going to use it for derivation purposes. We're not going to actually use this when you are solving problems. So I do want to remind you all of that. So 5, 4, 3, 2, 1. All right, so I do want to remind you before I show you anything with this, I want to remind you whenever you're doing stuff with energy that this is the bread and butter that you want to use. This is not what we're using right now. I just want to remind you, this is our bread and butter. Energy initial plus work equals energy final. The reason I'm doing this, though, is for derivation purposes. So if you all remember, work was the negative change in potential. We use that to derive mgy. That's how we derive the equation for mgy is doing this. Well, kind of went both ways, I suppose. So great. Good job, good job. What is the equation for work? So again, this is all just building together. We're going to use all of this to like derive the expression for the universal gravity, the universal energy due to gravity. Universal gravitational energy. There we go. We got there. Is work the integral of the kinetic energy dot the path you take? Is work the integral of force dot the path you take? Is work the negative integral of force dot the path you take? Or is work equal to the integral of the potential energy dot the path you take? Remember that dot is a dot product. It's a way of multiplying vectors, multiplies parts parallel.
Does the dot product like imply cosine?
Yeah. Yeah. The dot product turns into the magnitudes times cosine theta. The logic there is the cosine theta, which is parts parallel. Yeah. That was, it originally starts as this, and when we simplified it to that. Sometimes, at some point, you'll learn how to do the dot product. The way you do the dot product is you multiply the x components together, plus you multiply the y components together, plus you multiply the z components together. That's another way of doing the dot product. You'll learn about that in the future at some point. Cross product is awful how you do that one. You set up a matrix. You'll see when you see it. But we keep things simple for now. All right, I'll give you all 5 more seconds because either you know it or you don't. 5, 4, 3, 2, 1. Great job, everyone. The integral of f dot dl, it is the positive. So putting it all together, if work equals a negative change in potential, and work equals the integral of f dot dl, then if a equals b, then b equals c. A equals c. So we set them equal to each other. We then do the integral, so we set these two things equal to each other. We plug in our force due to gravity, universal gravity. And I bet you can guess the next slide that I'm going to ask you. There's an integral. Guess what I'm going to have you all do? The integral. Y'all can integrate that. This is not a complex integral. It looks like... So this is negative integral from R1 to R2 of G times M1 times M2 over R squared, and our path here is dr. That's the direction we're moving. We're going to move away from the Earth. We're going to find the work required to move away from the Earth. We're going to find the change in potential due to moving away from the Earth. Don't forget about that negative sign in front. That's a lot of that. Yes. Can you do an integral? That's the question. Okay. So why is it B and not A? That's not an answer. No. What is the solution to negative? Is it a negative? Okay. Why is there negative? Move the negative. What's the negative? You know what? I feel like it's... No. Yeah. So, are you cool with that? That was a definition. So, for now, just remember that was a and then that's a definition of work. So they're equal to each other. Right. So this is work, and this is work. So I just set this equal to this. And I just wrote it on the side to the other side. How's that feel? The work is negative changes. Yeah, so it is. It's positive change in kinetic, it's negative change in just sets that up. So work equals and work equals so this equals cos of 1 half initial square. This one will equal set these equal to each other. So therefore, 1 half and 5 squared minus 1 and the initial square equals mgy plus minus final. If I add the contours over here and I add the initial over here, you end up with final plus you end up arriving at so that's how it works. Anyway, so then from that, this is just an integral. I would say, what's the force that we care about this problem?
I thought the derivatives were by
Force to the graph.
So
So we're just gonna, hey, let's find the change potential due to this force. So I just chuck it into the equation and integrate. Yeah, no, I'm glad you asked this question. All right, we'll go like 10 more seconds. So we'll close it out in 5, 4, 3, 2, 1. As we solve this, it's going to be straightforward. You'll see. If it didn't make sense, it will. All right. So this is the negative integral of R1, R2. That is not R squared. All right. Pull out all the constants. G is a constant. Mass is a constant. Pull them all out. So negative G, M1, M2. And then we're going to integrate from R1 to R2 of 1 over R squared dr. So that's the only thing you're really integrating here, y'all. It's an integral of 1 over R squared. Very, straightforward integral. The way I do integrals is I think what function, if I took the derivative, would get me to this function. That's kind of what I do at this point. That's the logic I use. So what would get me an R squared on the bottom? A 1 over R would. So a G, M1, M2, and then we're going to have a 1 over R. If I take the derivative of 1 over R, it gets me 1 over R squared because the power gets reduced by 1 and, all those things. But you get another negative sign. You get another negative sign because if you take the derivative of that, it needs to kick out the negative. And again, do this integral however you want to do this integral, but that's the logic I use. So the negatives cancel. So long story short, you get G M1 M2 over R2 minus G M1 M2 over R1. There it is. How'd we do? Hey, that's pretty good. Okay. Don't worry, we got another question. According to this equation, where does it equal 0? Where do we want to set our 0 equal to? Remember, we always got to define where 0 is, so let's pick it based on the math. When does this equal 0? Is it when R is 0, which is at the surface? Is it when R is infinity? Or is it impossible to reach this? And we're always going to say the limit. Is it the limit as R goes to 0? Is it the limit as R goes to infinity? Try it out. When does this term go to 0? Is it when as R approaches 0? Is it, to go in the order, is it when R approaches infinity? Is it when R approaches 0? Or is it never? That's what these terms mean. Infinitely far away means the limit as R approaches infinity. Limit R approaches infinity. Is it the limit as R approaches 0? When does this equation equal 0? What do y'all think? Far away, really big number. Yeah, I put the limit here.
Zero. Yeah, we get all loads of reels out there. Yeah.
Alright, what's up here? Yeah, so that's what's in over the hill. Yeah, that's why I put the limit in So I put the limit as R32.
I don't know, people just seem like they're
Yeah,
wrong.
it's the same
So
thing.
say in one of those reviews where people are like,
So you always have to what
but then
number
that's
does it
where I
approach
just
as? If you divide by infinite small number.
I would rather
I reached out to you and then,
that's what I'm saying.
You
Like maybe the whole way is over.
That's approximation.
so I get top 3 and then I get well, I guess you could say top 3. I didn't do. I did
No, literally. Nina Brown. She was no rating.
Alright. 10 more seconds. 5, 4, 3, 2, 1. All right, so the key here, and I put the limits here to make math people happy. Physicists, we don't really care. Physicists are perfectly content dividing by infinity. We have no concerns with that because it's an approximation. So as r goes up, that goes down, and it approaches 0. Because remember, y'all, when you talk about potential energy, you have to decide where 0 is. When you talk about potential energy, so if you all remember your OG equation, the one that you all been using up to this point, it was MGY. Every single I'm using Y instead of H moving forward because I think it's more clear. You always have to decide where your 0 is. In this type of problem, we actually kind of have a set 0. We decide infinitely far away is 0 because it makes the math work really nice. When you all do UG equals MGY, you have to decide. But when it comes to planets, we say the potential energy is 0 when you're infinitely far away. Now, the question is, do you ever get infinitely far away? No. But do you actually need to get in? So this gets to an interesting philosophical question of what is infinite and all that jazz. Infinite's just a big number, y'all. And the example I give people for infinite, you can't get infinitely, like, look, no infinite surface exists. This is just the easiest one for me to showcase to you all. No infinite surface exists, but if I move my face really close to this board, it's an infinite board because I can't see the edges of it. If you can't see the edges of it, it's effectively infinite. So you can actually approximate many things as infinitely large or infinitely small if you're just close enough or far enough away from them, depending on what it is. So in this case, what is infinitely far away? Gosh, that's a good question. What do you like? How far away do you think you need to get? If we're like Jupiter, you think that's infinitely far from the Earth? That's probably far enough that you don't have to care about the Earth, right?
I think it has an effect of orbital resonance.
Okay.
So you could say the nearest star if you want.
Nearest, that's it. Yeah, you can go all the way to the nearest star if you want to, or like maybe leave the solar system if you want to be like. But you probably don't even need to get that far. I bet you if you're at Jupiter, you don't need to worry about the gravitational force that the Earth is acting on you. So, anywho, boom. There's the okay. So there's a negative sign.
Yeah.
There's a negative sign because.
R2.
Yeah, remember, it's where you start and where you end. It's where you start and where you end. Where do we say we're ending in this problem? If we end at infinite, what happens to my first term? So yeah, grabbing this equation and chucking it over here. If we make R2 infinity, where we end, this term goes away. And the gravitation, and this is going to be really weird to you all, according the universal gravitational equation is always a negative value. You always have a negative gravitational potential energy, which is like, what's that mean? It doesn't matter that it's negative, y'all. I'm going to show you all, it only matters how it compares to somewhere else, if it's bigger or a smaller number. But the negative, that's what the math kicks out. And that's fine. A negative value just means -5 is smaller than -3. That's all you care about. You just care about them relative to each other. The negative doesn't tell you anything. Except, -5 is smaller than -2. That's all you need to really care about here. Oh, and you got to be farther away from the surface of the object. If you're inside your object, this equation doesn't work.
Yeah.
So, case in point, you can't use this inside the Earth's crust. Yeah. Because then the outside of the Earth's crust is also pulling on you, and that gets tricky. Fun fact, if you're at the center of the Earth, the force of... Okay, this might be kind of expected. The force of gravity at the center of the Earth is 0. Because you get pulled in all directions equally, so it all cancels out. So if you all have made it to the center of the Earth and you didn't get fried by the heat and stuff like that, you'd actually be weightless. Yeah. So if you made a hole through the center of the Earth, if you somehow can reach it to the middle, you'd be weightless, which is really weird. And that's because everything's pulling on you equally in all directions. So it all cancels out. Every single atom of your body is getting pulled in every single direction equally, and all the forces cancel out, and you're fine. It doesn't tear you apart. Yeah. Yeah. Yeah, you would have some, but it would. I think the effects would mostly cancel. Like the distances between the top of your head would be so small. It only makes a difference of going to a black hole, I think, where the gravitational force is so strong that between your head and your foot, it could be. You could get spaghettified. Yeah, the whole. Yeah, and yeah, no, for sure. So there you go, y'all. And you're like, why am I doing this? We're gonna get to do a really, really cool calculation. I think it's a really cool calculation. We are gonna calculate the escape velocity, which is a phrase you might have heard before, and it's a really, really simple thing to calculate. It's how fast you need to be going to escape Earth. If you go straight up with this velocity, you will never come back to Earth. Ever. It doesn't matter if you're accelerating. It just says if an object is going this fast at any point, it will never get pulled back down to Earth. I don't care the trajectory of your object. I don't care if it's straight up or to the side or whatever. If you are going this fast, you're leaving the Earth. And you can also apply this to all the things. So there's an escape velocity of the entire solar system. How fast you need to be going so that the solar system never pulls you back. Because remember, gravity is always pulling you back. But at some point, you can go fast enough that gravity will never be able to pull you back down to Earth. You're kind of outrunning the effects of gravity, effectively. Really, really cool thing. It's called escape velocity. You do not need the escape velocity to orbit the planet. Actually, things orbiting the planet have not escaped Earth's gravity. They're forever being pulled by Earth's gravity. The escape velocity means you never come back. You're not orbiting the planet. You are gone. You are leaving. You are never coming back unless you turn that rocket around and start turning on the thrusters. So, anyway, we're going to do that in a second. It's going to be this problem. You will calculate the velocity needed to escape it. But before we get there, according to this equation, UG equals G M1 M2 over R. And we'll chuck a negative sign in front of it. According to this equation that we just found, what happens to the gravitational potential energy as you get further from the object? As you get further from the object, according to this, And please, 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 don't do math. Make up numbers here. Make up numbers and compare them. Compare it if R is 5 and compare it if R is 10. That is the way that you guarantee you don't mess this problem up. If R is 5 and R is 10, what happens? Does it get bigger or smaller? When R is 10, how does the value compare to when R is 5? You do not have to do this calculation, but if you do not do this calculation, you probably got a 50-50 shot of getting this right.
Do you mean like the absolute value?
I do not mean the absolute value. I do not mean the absolute value. Take the number it spits out. Oh, no, that's very sad. There's a negative sign. I accidentally sent this out without the negative sign. There is a negative sign. Please, please, please make sure you have that negative sign. Or it doesn't work. The correct equation is a negative sign. If you do not account for that negative sign, you're going to get the wrong answer. Negative sign matters a lot.
Negative.
What'd y'all get? Okay, you did not.
Bigger.
What number?
Okay.
Okay.
So, and obviously bigger is actually smaller, but it's negative.
Okay. It's weird. Well, actually, okay. It's not weird. It's what you expect, actually. You expect the gravitational potential energy to get higher. But, it's weird stuff. Because I guess it does match what you expect. No, it matches what you expect. All right, give y'all like 10 more seconds. All right, 5, 4, 3, 2, 1. All right, I have just, to make it a little bit simpler, I made R infinite. R infinite. We decided when R is infinite, if you plug that into this equation, you get -0, which, look, that's just 0. There's no such thing as -0. All right, great. I don't care what number your initial one is. You're going to get a negative number. I don't care what that, you can plug in the math and get the number. What's bigger, 0 or a negative? 0. So look, it works the way you expect it to. But it's a weird thing because here's the graph of this, y'all. If we draw a graph of the potential energy, it looks like this. You're existing in the negative quadrant. So it is increasing, but it's all the negative values, and that's because how we chose 0 and all that. And that's fine. There's no problem with this. Negative potential energy doesn't mean anything. You just compare the values and say which one's bigger. And which way will things move? Will they go from high energy to low energy or low energy to high energy? Let's see. This lion, I don't have demo duck, so my lion's my stand-in. Which way is he going to fall? Down. Is that a lower potential energy or a higher potential energy? Lower. One of the rules of the universe, y'all, is everything moves to lower potential energy. That explains almost everything that happens naturally out there. Things want to go to lower potential energy. It's one of those rules of the universe that you can use to explain almost any single interaction. It's the reason that ions move in your body across the cell walls. I think it's called I don't know if it's osmosis or what. Diffusion. Diffusion. Ion transport across cell walls is. Your body is designed to make use of this. Everything is designed. Moves to lower energy. Okay. And then I just wanted to show you all this. This is just a really interesting plot that shows you the acceleration due to gravity of the Earth. This is not energy. This is acceleration. So this is just like a completely separate thing. It's kind of cool to see. So remember I told you all these equations only work when you're farther away from the Earth's surface. So this is the equation for the acceleration due to gravity. A equals gm over r. Fantastic. But look how crazy this thing is. When you're inside the Earth, you have to account for, I don't know why you would care about this. We're not going inside the Earth anytime soon. If y'all haven't, we've never actually broken through the crust. Like digging deep holes. If you were anything like me, I think I don't know if every kid has this. Every kid thinks about if I just keep digging, I'll make it to China. Yeah, I don't know why. That's I don't know how common that experience is, but I remember that being a thing of like, you just keep digging and digging, and every kid thinks you just keep digging, you make it to, yeah, no one's, it gets really hard, y'all. It gets hot. Your drill starts to melt. There's lots of problems with it. But it is cool to see that the acceleration, look how weird it is. Because the Earth is not a constant density, so inside it is literally a hot mess. But it's really hard to actually calculate it because the density varies and all that kind of stuff. Great news. I'm never going to have you find the acceleration due to gravity inside the Earth because what's the benefit? I don't know what the value would be there. But it's cool to see this graph and just show changes. All right. Okay. So now we get to the problem that I think is super, super cool. How fast do you need to be going? Not so that you'll orbit the Earth. That's not the question here. Not so that you'll orbit the Earth. How fast do you need to be going so that you will only go farther from the Earth. Every single second you're going to go farther from the Earth. And you will never get closer ever again. You will never come back home unless you turn that rocket around and actually provide some thrust and some acceleration to cancel out some of that velocity. So what is the escape velocity needed to leave Earth's gravitational pull? The Earth has a mass of that and a radius of that, and that's all you need to know. That's the only two variables you need to know to figure out how fast you need to be going, which is cool. I'm going to give you all some time. You can write down your givens. You can write down what you're solving for. What I want you all to try to figure out, how the heck am I going to solve this problem? And my recommendation to you all is you have a toolbox. We've done a variety of tools this semester. Kinematics, forces, momentum, energy. Which of those toolboxes are you going to pull from to solve this problem? Are you going to pull from energy? Are you going to pull from momentum? Are you going to pull from kinematics? Are you going to pull from forces? See, I'll give you all some time to think about what is the toolbox we're going to pull from to solve this based on what we have. This isn't going in a circle.
Oh, it is.
This one is not going in a circle. We're going straight up and then going back.
I guess you can move, yeah.
Okay. I remember when we derived it.
I would put an image on where you must drive what toolbox. I recommend drawing a picture. Draw where you start and draw where you end. Take the extremes. Where do you start and where do you end? And that might help you. And draw arrows on it and all that jazz. What toolbox do y'all think
I remember
So that works for going certain. We're literally just straight up, never going back. The path of this will be a straight line. Well, I mean, it might mark slightly, but it'll never stop. So there's the Earth. Here's us on the Earth. Am I moving in the beginning? Do I need to be moving? Question, y'all. If I'm not moving in the beginning, am I going anywhere? No, I need to be moving in the beginning. I'm not going to go anywhere unless I'm moving. Like, nothing's going to happen. So I need to be moving. That's my initial. And then my final is going to get a little tricky to draw. Here's the Earth. Where's the extreme location? If I'm escaped Earth's gravitational pull, where do we want to move? Go extreme. I want to be infinitely far away. Now, I can't draw infinitely far on this picture, so I don't know. I'm somewhere over here off the slide. I'm not going to leave it there. I am infinitely far away. And if I'm infinitely far away, am I going to feel Earth's gravity anymore? No. Do I need to be moving anymore to escape it? No. So, in the beginning, I am moving, and at the end, I am infinitely far away. And we go through our toolbox, and we decide what we're going to use. Kinematics. Do you all know anything about its velocity? Do you know anything about the acceleration it's experiencing? No, I mean, I guess you could use you maybe could use kinematics and say that the acceleration is g over mr, and but then you'd have to integrate that, and I don't think you want to do that. I haven't taught you all how to do an equation where the acceleration is changing with respect to time. So probably not. Okay, I guess you could integrate it and get the velocity equation, the position equation.
Acceleration changes with respect to r.
Yeah, I was like, I guess you could integrate acceleration and get the velocity as respect to time. But that, I don't know if that worked. All right, great. Kinematics out the window. Forces. We do have the force. We do have the equation for force, but same problem, y'all. Guess what you'd have to do with that? You'd have to integrate it, and you'd have to also figure out how that relates to velocity. Which, again, you can maybe get creative, but that's more work than we need to do. Momentum. Is there any collisions happening here? They do split from each other. I wonder if you could use that. I don't think it would work very well. All right, let's look at our last one. Energy. Can we use energy? Let's just think through that one. Remember, y'all, the magic equation. Energy initial equals energy initial plus work equals energy final. All right. In the beginning, what kind of energy do we have? We have potential energy in the beginning. Oh, and before I even start doing that, is there any work being done? Air resistance, friction? Is there any rockets? Are we constantly This is not constantly accelerating. It just says I kick something this fast. And then we see what happens. There's no work. So what energy do I start with? Gravitational potential. What other energy do I start with? Kinetic. Equal. Oh, is there any springs? Any springs involved? No, there's no springs involved. All right. What energy do I end with? Am I moving? So at the end, we're going to find the minimum you need. The minimum you need to escape it. So it's not going to be moving at the end. We're finding the minimum kinetic energy you need to escape it. So when you reach infinitely far away, you finally come to a stop. You have escaped. You're not getting pulled back. So actually, your final velocity is 0. You're not moving. Do we have potential energy infinitely far away? If r is infinite, if this distance is infinite, we have no potential. That's the equation. And you may be like, what the heck? How is this going to work? How do I add two numbers and get 0? Remember, y'all, this equation's negative. Remember, y'all, the equation for potential energy is negative, so you're going to have a negative plus a positive equals 0. All right. Try it out, y'all. I've kind of given you try it out. Use this information. Remember, r here is not the distance from the surface. That's my r initial, distance from the center of the Earth. Try it out. Try it out. Play around with this, y'all. And this is literally how the escape velocity is calculated for Earth. It's actually a quite simple setup once you realize its energy. Write down your givens, write down your missing, find the value. Nice. Yeah, good. It's a really, really fun and cool problem, in my opinion. I'm biased. Write it out and see why. Now I'm just going to write it see why that happens. That's a great question. But when you set up a whole equation, one side So I was like, yeah, just start going through it, what's given, what's missing, build the equation, the entire equation. This one you gotta build it to see all the so you got your givens, or what we solve for.
How do I not see this?
So we have this equation. I gave you one. Go ahead and actually break it. So build the equation with as many things as you can.
You're like, I'm a zero.
Yeah. Yep. They do. If you have a shared term, what can you do? Not complain. You did, I guess. You can pull them out. And then what do we have? We have a glorious trash can that is 0. Just chuck it into the trash can. Oh, yeah. What's the answer? All right, there's the answer, y'all.
In this case, you can say whatever that you want, but you're going to have an n. This is how fast you're done moving, so whatever passes you.
Yeah, so build it, y'all. If you have questions, just trust me. Start building the equation. That's where the fun stuff comes in. When you get to see things that I haven't shown you yet. So, from this, we know the mass of Earth. So, the mass of Earth is 5.96 times 10 to the 24 kilograms. We know the radius of the Earth. And what are we solving for? We're solving for the initial velocity. How fast you need to be going to fly off and never come back. Okay? Now, if you notice the equations I gave you all, there's no V in it currently. Where is the V going to show up? Kinetic energy. So you all just need to actually like build this equation out. So we get negative G, M1, and the mass 2 is going to be the Earth. The Earth is the one causing the gravitational energy. The mass 1 is experiencing it. Plus 1/2 M1 V squared. Again, you just got to build it out. You just got to build it to make it happen. And I got a really, really good question. Don't we need to know the mass of my object? That is a valid question because in this equation, it looks like we have it. Why does it not matter? We can pull it out. We have the glorious trash can that is 0. 0 is the magical trash can that if you can pull a term out, you can chuck it into that 0 and it'll never... So look, if both of these terms have mass 1, chuck it into the 0. Chuck it into the trash can that is 0. You can factor out that M1 and it goes into the trash can. And now it's just you've got everything you need. And then you just do the math. So negative, if we rearrange this, we get negative G M-E over R. You know, I'm just going to move things over. Equals 1/2 V initial squared. So V initial equals the square root of 2 times G M-E over the radius of the Earth. And then I will plug in the numbers. And you get 1.124 times 10 to the 4, which is 11200. You need to be going 11,200 meters per second, which is a silly fast number. The speed of sound is 343 meters per second. So you need to be going, if we divide that number, 11,200 divided by the speed of sound, you need to be going Mach 33 to escape the Earth. Now, here's the thing. This can happen at any point. You can do this in space where there's no air resistance. If you go Mach 33 on Earth, you're going to get vaporized. Like, unless you're made of tungsten, and even tungsten might not survive. I don't know if y'all have ever heard about the fastest object on Earth. The fastest object on Earth is not one that you would ever expect. It's hypothesized to be the fastest object on Earth. Yeah, it was a manhole cover. Yeah. So the fastest object, and it's very likely this thing did not survive. I don't know. I think they've done math. It may or may not have survived. So back in the day, nuclear bombs were a thing. I mean, they're still a thing. Back in the day, nuclear bombs were a thing. Still are. And they did nuclear testing. Now, the thing with nuclear testing is that it emits a bunch of radiation into the atmosphere, which then kind of makes its way around Earth, and people don't tend to like that. They also don't like it because then satellites can pick up that nuclear testing is happening, and other countries can spy on you and determine what you're doing. It's pretty noticeable when a bomb that large goes off in space, even. So what do they start doing? They start doing nuclear testing underground, where you can't see it anymore and where the radiation is contained and all of that jazz. And so to that end, I believe it was the Russians. It might have been the Russians, might have been us. I have to check. They did nuclear testing underground, and there was like a pipe for the exhaust because, you got a lot of pressure in it. You need somewhere for it to release still, which I guess release radiation, whatever. Manhole cover over that thing. All the energy from that nuclear bomb gets channeled through this thin tube into the manhole cover at the top, and that manhole cover gets ejected at... The velocity is so, let's just look it up real quick. I don't remember the number. It's something stupid. It's so fast they only capture it on like one frame. But the time between the frames is like, so they can get an approximation. It's probably going faster than this actually. It was far above the escape velocity. Fastest object ever. Fastest man. Oh, okay. Fastest object on Earth. We have things in space that go really fast, but that's cheating. They don't have air drag. Fastest object on Earth. Yeah. Okay, light is cheating too. That's stupid. Fastest object ever built. Where are you, manhole cover? Yeah, I'm just going to chuck manhole cover in there. Underground testing, 1957. Nevada. So it was the U.S. For good or for bad. Take that how you want. I don't really care. All right, so they said 125 1,000 miles per hour. And yeah, it's really, feel free to check it out. Again, it's really, really cool. They literally have like a single frame of video of the thing in the frame, and then it's gone. It's not like they had high speed enough cameras to catch this.
Especially if it's being launched with this facing up, it encounters maximum air resistance.
But look at that! It's 4 times the escape velocity of the Earth so easily.
And within like
Assuming it even survived. I mean, the thing was traveling so fast that one, it's going to heat up and like melt to oblivion, but also it's going so fast it might not have the time to heat up. Like, so you end up with a weird situation where, and I don't know what they actually said, if they think it survived or not. Globules of it would have survived, presumably. They may have like atomized or vaporized and whatever. But it's fun. All right, so last thing before we enter our break, let me just calculate this somewhere so that we can say I did my due diligence. But yeah, clearly it's really hard to reach the speed on Earth. But in space, it's not that challenging. Okay, it is and isn't. If you have enough fuel, it's not that challenging. Fuel's expensive, though. Mainly the weight to get it to space. All right, so step 4, V initial equals the square root of 2 times 6.674 e to the minus 11 times the mass of the Earth, which is 5.96 e to the 24. So there's 2 takeaways from this problem. 1, it is possible to escape Earth's gravity. 2, it's really hard to escape Earth's gravity. Orbits aren't escaping Earth's gravity. They're just outrunning it. But the second they slow down a bit, they start to fall right back down to Earth. So this is if you never want to come back. You say, I'm done with Earth. Get out of here. I don't want to see you anymore. All right. There you go. All right. Take a breather, y'all. That is everything I wanted to teach you all about gravity, and now I want to turn to center mass. There's basically just 3 equations I taught you all: universal gravity force, acceleration, and potential. Take a breather.
I love when all my professors are like everyone's like, oh, this is
Yeah, I think they did some math on it. I don't know if they said it survived or not. Well, did the manhole cover survive? I think it likely burned up. See, yeah, you run into 2 situations. One, it's going to get hot really, really quickly. But also, it's not going to be in the air that long. So, like, you get a really weird balance of...
But that's also from sea level. That's what
yeah. The manhole cover was? What's that? Sure. It's a giant steel disc though, which
If it was a 7,
yeah, it would turn into a semi-sphere real quick.
unless it rotated.
That thing wasn't gonna.
Because stable was for launch. But also, if it's going away,
So we're gonna run into the interesting situation where we're finished pretty early. Not like today, but like I might finish everything today. So that gives us the half a class on Tuesday.
And then Thursday. Yeah, huh?
And it's tempting to immediately start doing stuff that we're not into. Start doing tests. But no one likes that.
Well, it's not urgent.
Everyone's focused.
So if you all have ideas, and it could just be you just started the lab. Which I also have.
Like the whole paper that you have to go through.
Yeah, this guy was.
Oh, like as a whole.
On a full film because I don't think we had. We all didn't find it. Good. You all check that at the end. It's got hanging masses. And also, no, that's one of the because if I can have someone hang powder that I could do
But I think it's probably just a bunch of masses. Yeah, it's just a bunch of masses. Oh, there's aluminum rods, but I don't know what we'd hang them on. No. All right. It is good, I guess. My current plan is to have the meter stick, and if you all could find something we could. A pencil's probably good because I need something that doesn't make it have too much of an angle because they're gonna rest the masses on it, and I don't want them to slide around a bunch. So if it's a nice gentle slope, the friction of the block should be enough to keep it on the meter stick. I don't know. All right. We shall resume. All right, so I have covered, just to reiterate, there's basically 3 things I taught y'all. I taught you all, let's scroll back up. I taught you all the universal force of gravity. Boom. There it is. I taught you all the acceleration due to gravity. There it is. Control C, Control V. And then I taught you all the potential energy due to gravity. And we did stuff with it. And that's really the bread and butter. Like, it's all about universal gravity. And look, I don't know how many of y'all are doing stuff in space or anything like that. But the reason I spent the time on this, the reason I thought it was worthwhile, is because we are entering an age where more space stuff is happening. More things are going to space. It's becoming more relevant. And these 3 equations basically can tell you everything you need to know. They don't tell you about thrust and stuff like that, but they at least tell you how the planetary bodies works. All right. The next thing I'm going to teach you all is going to be very, very relevant for civil engineers, mechanical engineers, aerospace engineers, and, as usual, electrical engineers and stuff like that. Center mass. Center mass is the next chunk of content, and we may or may not finish it today, which leaves us with like a bunch of extra time to prepare for the next exam. Here's the intro. If I had a triangular shaped roof with a constant density, where would I place a single vertical beam to support that object? Approximately. Where does it balance nicely? At point A, all the way to the left, point B, point C, point D. We're not bolting it, y'all. We're just resting it on it.
But I guess being more towards the center. Yeah. It is definitely. Because think about it, if this is my phone, it has
That's a problem. I need some broad. But pencil, I guess, is nice.
So. All right, 10 more seconds. Fairly straightforward question. All right, in 5, 4, 3, 2, and 1. And then I walk slowly so you check the 8 more seconds. All right. Pretty much everyone got this right. Point B. Why is it point B? And that's what I'm going to teach you all, because you all know this intuitively. The vast, y'all tell me, why the heck did you choose point B? I haven't taught you any physics about this. Why?
Because if you have a single density and you're you don't want to have bigger weight, big weight, small, this longer side with the same amount.
Yeah, so this side's longer, but it's got kind of less mass at the end, and this side's bigger, but it's not as far away. And again, this just comes from your all's experiences in life. You all probably played around with things and balance it on your finger, and you found that when there's more stuff on one side, you got to counteract that. This is just from your all's experiences. I'm going to teach you all the math today, and we're going to learn that when it comes to linear motion, only linear motion, when it comes to linear motion, moving left, right, up, down in a straight line, you can approximate this object as a single blob right here. And that single blob is called the center of mass. You can take all of that mass and pretend that this object is the exact same as that red blob I drew. And as far as linear motion is concerned, all the physics works out the same. Well, yeah, Angelina, you have a cool video for that at some point.
I need to pull it up.
Yeah, there's a cool video that shows this that Angelina found. Sadly, we can't show you all. We don't have a demo for this, so we have to show you a video of it. But it is a really, really cool demonstration of how you can approximate a complex object as a single point. Only for linear, when I say linear motion, not rotating stuff, not spinning stuff. You cannot do this for spinning. If it's spinning, it's way more. You got to do other things. We'll get to that eventually. That's what I teach you all after exam 2. Yeah. Unless it's symmetric. All right. Do you have a HDMI port?
Yes.
Cool. All right. So she's gonna hijack this thing, and then if you're online, you don't get to see the video, I guess. Angelina can maybe send that as an announcement, so y'all can check it out on your own. The lion. He's lying down.
So can't we not make this start from the beginning? Okay, there we go. Yes, unfortunately we cannot zoom in.
Oh, you could probably shift it back so you don't have to hold your laptop.
Oh, because it'll rotate around its center of mass.
Yeah. All right, so here's an object. It's a tennis racket that has really, tennis rackets are complex. One day the tennis racket will show up. Just trust me.
There we go.
Okay, so you might have to. I'm gonna let you.
Yeah, it's gonna.
This is your
loop
video.
back around.
You explain it.
We're gonna wait for the video to loop back around.
It's the joy of Instagram where you can't rewind or fast forward because marketing or something. I don't know.
So you spend more time on it. Alright, so the tennis racket, it flies, it's doing weird stuff, and it's hard to understand what it's doing or track that motion. In slow-mo. But if we turn the lights off and we mark the center of mass, it's just a perfect point moving a perfect projectile. and that's a lot easier to do the math for than whatever spinning it was doing.
Yeah. You don't care that it's spinning. Like, okay, there is things you care about, but in the case of something flying through the air, spinning doesn't actually, assuming no air resistance, spinning doesn't matter. If it's spinning, air matters. So it's the same exact object, they just turned on a black light so you can only see that little orange dot. It's the same exact object in every single video. But yeah, when they do the black light, you see that the path of the motion is parabolic even though it's spinning. And that's the center of mass. And that center of mass is super, super cool and super, super useful. So, yeah, so it's cool stuff. We'll post the video and give them some more views or something. But center of mass is super, super handy to make a complex problem much easier. Believe it or not, every single problem you all been doing this entire class has assumed that you're working with the center of mass. Every single problem I've had you all do, you didn't care what the shape of the car was. You did not care what the, if it was spinning or not. Never did anyone ask me in this class, is that object spinning? No one in this class asked, what's the shape of that object that's being thrown? Because you didn't care. Because you were secretly caring about the center of mass. You were secretly looking at the center of mass the entire time. So now let's actually calculate center of mass, and I'll show you all a slide with the derivation. And as always, it's going to look bad. One step at a time. One step at a time. We look at the beginning. Don't look at the whole thing. Here, I'm going to zoom in so you don't get intimidated. All right. Force equals mass times acceleration. And it might look like I skipped a step, so I'll kind of remind you all. This is something we learned from momentum. If you all remember, we derived this, so m equals dv dt. So if you just do m times dv dt, that is the change in momentum. Okay? Mass times change in velocity, that's the change in momentum. So that's one that we used before. I'm not going to spend too much time on it. Great. And then I sum it all up because maybe I have multiple objects. Maybe I have 5 objects I'm doing this for. Pull out the dt. Then we remember that momentum is m times v. V is defined as the derivative of dr dt. Great. And so then we just put that all together, y'all. We then just take this p. Where do we want to put it? Different color. We take this p and we put it here. So we put those things. If they're both p, then we can take this term and shove it right there. Great. You pull out the time derivative. So you get the second time derivative. And it looks all sorts of crazy, but you get this expression that if I sum up all the masses times the radius, and you're like, what, this 1 over m term? Let me just highlight that real quick because I kind of skipped past that. Just move that m to the other side. Ta-da! This is conservation. This is just rearranging it. This is deriving. This is how you get center of mass of an object. You get a bunch of spots on an object, and if you average them, it matters how far away they are. It matters how much mass they have, and then we kind of normalize it by the total mass of the system. This equation down here is the one that we're going to be using for the next however long it takes me to teach it all. And don't worry, the next slide has center of mass, all nice, but I always want to show you all where they come from because it's not made, like, it feels made up at times. Every single derivation I show you all is using equations that you're using all the time. None of the math is super complex. Every single individual step, every single one you're capable of understanding. And yeah, my goal is to connect that equation that I just showed you to that triangle. Because everyone knows how the triangle works. I just need you all to connect that, what you currently know, to the new equation. Oh, and I'm also going to warn you, we do have to split things into x and y. She's learning about we're potty training. Something. Picture of my daughter. That's good. All right, the blinky blink. Oh, wait a little bit longer. Yeah. Oh, Leo, he needs you. He wants to ask how your day is. All right, cool. So, long story short, look, this works worse than it is. Don't get overwhelmed. There's a lot of stuff going on here. It looks worse than it is. I'm just going to zoom in on this equation for now so you don't get overwhelmed. And you look at this equation, you're going to say it's gross. It's exactly what we explained with the triangle, y'all. How far away you are from the thing matters. Remember when y'all are balancing stuff, things that are farther away kind of pull it down more. That's one way of thinking about it. How much is hanging from it matters. That's the mass term. And then we just got to kind of cancel out the fact that we're adding up all the masses. We're going to kind of cancel out all the masses. Because we're not finding we're finding where the center of mass is located. That's the whole point of this equation. Where is the center of mass? So if I add all the masses, I need to cancel out all the masses. Okay? So that I just get kind of location. That's what's going on here. This looks way worse than it is. Because you got a summation sign and you got these J symbols. It literally says add up all the objects and how far take an object, multiply how far away it is. Add the next object and how far away it is. Add the next object and how far away it is. Divide by m and you get where the center of mass is located. We will probably not do this with the triangle because it's actually we'll get to continuous objects at some point. So there's a picture of it. It's a weighted average. So for those that do statistics or anything like that, it's just a weighted average. X and Y are independent of each other. So we're going to do the center of mass in the X location. And we're going to do the center of mass in the Y location. Because things can be 3-dimensional, 2-dimensional, 3-dimensional. But it's a super, super handy and helpful tool to be able to take a really complex system and make it simple. I mean, this system looks really complicated. I got 3 objects. But I can pretend like they're one object located here. That's why this is so handy. And it lets you take really, really, really complex geometries, really, really complex objects, and make them into one blob located at the center of mass. Okay? So, yeah, a bunch of things here. We're going to practice it. As always, when you see an equation for the first time, it might look overwhelming. But once we start to use it, you'll become best friends. I don't know if you'll be best friends with it, but you'll at least be on better terms. You'll get to know it. You know, when you meet a stranger, it might be intimidating. But once you get to know them, know their details and things like that, it all makes sense. They may not make sense, but you might not fully be able to understand them. But math is a little bit easier than people. So math follows rules. People do and don't follow rules. Yeah. So anyway, at least we're not working with people, y'all. Could be worse. You can't account for all the variables involved in an individual. So anyway, as always, we're going to start, simple. And we'll work our way up to complex. But before I even do all that, I'm going to show you all that this equation is one that you might know how to do. And we're going to look at it in a different context. So it says a weighted average. So we're going to look at a weighted average that you're more familiar with. And that's GPA. And we're going to see that you use the same equation for GPA as you do for center mass. So again, trying to connect. So much of teaching is trying to connect a new concept to one you already know. And then you stretch your brain a little bit. And the next time I can utilize that new stretched part and so on and so forth. That's pretty much all learning. You got to connect it to something you know. Otherwise, it's not going to settle. All right. So here you go. I'm not going to even tell you how to do this. You all might, so this is something you might have done before though. What would be the GPA given the following scores and credits? Not a physics problem, but it's the exact same math that you're going to do for center mass. So I had a 4.0 GPA in my physics class, and that's 4 credit hours. My history class, I got a 3.0 GPA. I mean, this is... So, the numbers here are a little funny. Yeah, which is also their masses.
Yeah.
So again, showing you all that you probably can do this, even if that equation, maybe or maybe not, but it's a good exercise. It's also good academic exercise for you. So 4.0 in physics, but it was worth 4 credit hours. It was weighted more, like there's more to it. History was 3 GPA, but it was 3 credit hours, and underwater basket weaving was 2. You got a C in the class because you were too focused on physics. And you neglected your 5 credit hour underwater basket weaving class. What is the weighted GPA for this class? I.e., what would be your GPA after taking these 3 classes? This is what UCF calculates for you all. So some classes carry more weight because of the more credit hours. More credit hours, you gotta weight them. That's one way I guess you could do it. You could do it by. So weight each GPA, so that 4.0 GPA gets applied to the 4 that counts. And then the 3.0 gets 3 credit hours, so it gets kind of weighted by 3. And underwater basket weaving gets weighted by 5. But then you're going to end up with a really big number, right? So how do I standardize that? How am I going to kind of divide that so I have kind of an overall... So I'm going to give you all a little bit longer, then I'll give you all some hints. Hey, people are getting the answer. I don't know how much of it's like... I hope you all are figuring it out on your own kind of calculations. If you're using other things, that's fine. But it is, people are at least getting an answer, which is cool. And it might just be the one that's the most obvious. You might be intuitively figuring it out. So, this credit is my weighting kind of thing. Or sorry, the GPA, I guess you could say, is the weighting. So, how do I want to phrase this? If you're taking a more credit hour class, the GPA kind of carries bigger weight to it. So, you're going to kind of get the GPA for the credits. So you're going to take this number, the credits, and you're going to multiply it so that they all kind of get weighted. Your GPAs are all getting weighted. That way you're accounting for the credit hours. But here's the problem. Then you're going to add all that together. You're going to add all that together to kind of give you your overall, but then you're going to end up with a problem. Is that going to give you your overall GPA? No. What do we need to account for? We got to account for like how many credits you've taken overall. So how am I going to account for that? Yep, so I'm going to multiply this, and then I'm going to add these together. Add it all together, but then I have to account for how many credits I've taken. So you divide by the total number of credits. All right, I'll give you all a few more seconds to try this out, and then I'll walk through the math. And I'll show you all, this is literally a calculation of center of mass. If I just change the variables, it'd be center of mass. All right, so 5, 4, 3, 2, 1. And this is literally how, this is a weighted average. This is how your GPA is calculated in college. Probably good for y'all to know. All right, so I'm going to do 4 times 4 plus 3 times 3 plus 2 times 5. And And that gives me kind of like an overall measure of like my GPA. But I have to standardize that by what's my thing that's kind of like weighting it. It's how many credits you've taken. You divide it by the total number of credits that you've taken. If you all do this math, so you get 16 plus 9 plus 10 divided by 12, which equals 35 divided by 12. And you all pretty much got this. And y'all, this is literally the center of mass calculation. Replace this. This is my mass. This is where I'm located, how far along I am, how far I made it. The center of mass equation is 1 over m times the sum of mr. M times r. It's exactly what you all just did here. You multiplied m times r, you added them all up, and then you divided it by the sum of the mass. That's center of mass. It's the same exact thing. You weight them based on how far away they are. You then divide by all the mass to cancel it out. And ta-da, it's the same thing. It's a weighted average of where you're located. Okay, am I immediately... Well, this is a little unfortunate, I guess. I said I'd start simple. But we're just gonna straight jump to a two-dimensional problem. Let's see. Do I have a two-dimensional one that I can start with? Let me see. I'm not gonna lie. Okay, this one is two-dimensional, but it looks way worse. So let's start with one with a picture. I think, ironically, even though this is two-dimensional, I think it's gonna be easier for us. You all pick. Would you all rather do Earth, Moon, or would you rather do the one with the picture? I don't really care. I mean, we're gonna do both. You like pictures? All right. You know what? We're going to do this one, and I'm going to draw a picture. How about that, right? The best of both. We got so much time, y'all. So we can take things slow. I'm going to draw the picture for you all. Find the center of mass for the Earth-Moon system using Earth's center as the origin. The mass of the Earth is 5.97 times 10 to the 24. The mass of the Moon is 7.36 times 10 to the 22. And the distance from the Earth to the Moon is 3.82 times 10 to the 8 meters. If the radius of the Earth is 6.37 times 10 to the 6, how far away is the center of mass from Earth's surface? Okay. And I have to be careful here. I'm a little worried with one of these numbers, so we're going to play around with it and see which one works. Yeah, that's what I'm like. It says the distance from the Earth to the Moon. I don't know if that's from the surface of the Earth to the Moon or the center of the Earth to the Moon. All right. I'm going to draw a picture. There's the Earth. There's the Moon. I'm going to fact check something real quick to make certain I don't lie to y'all. Distance from Moon to Earth in meters. Great. And that's from the center of the Earth. No. 384. Yeah, it seems to be center to center. 384. Ooh, 382. That's fine. Okay. No, we do care about it. Okay, so this problem is subtle. So I'm going to draw a picture of this because the wording here is not ideal. The radius of the Earth is 6.37 times 10 to the 6. I then am giving you the distance from the surface of the Earth. And I think this is stupid. Yeah. Yeah, so we're just going to do that. I'm going to reword this problem on the fly. What did you say it was? 3.85? Yep. We're going to nix that. I'm going to make your all's life easier because I think the wording here is not clear enough. 3.85 times 10 to the 6, 8. All right. We have two objects. They are perfect spheres, which means we don't need to care about the up and down components. We are going to find the center of mass, which you may be like, why do we care about the center of mass? The fun fact about this is that the moon doesn't orbit the Earth. The moon orbits the center of mass of the Earth-Moon system. And the Earth actually is orbiting the center of mass of the Earth-Moon system. So what's weird there is it's not like the moon is just like orbiting the Earth. They're both orbiting a single point, which is not the center of the Earth. Which is weird. But that's the reality. All right. Mass of Earth equals 5.97 times 10 to the 24 kilograms. Mass of Moon equals 7.36 times 10 to the 22 kilograms. And we have the distance, we're going to call it of the moon. I don't know. Yeah, that's fine. It's on the picture, so it'll make sense when you look at it later. 3.85 times 10 to the 8 meters. We also know the radius of the Earth, but I made your life easier so you don't have to worry about it. Okay. Step 2, what are we solving for? We're solving for the center of mass. Okay. Before I start jumping into calculations, I need to remind you all of something. How far is the line from me? No, let me rephrase that. Where's the line located? If you all gave me a number, where would you all say it's located?
1 meter away from you.
1 meter, and yeah, you can't just say 1 meter, 1 meter away from me. Anytime you all talk about location, anytime you all talk about a position, center of mass is a position. It's a spot in space. You have to have a reference. From where? From where is this measured? Where, remember, you all been doing this in all your labs. You all had to set where the 0 location is. We've been setting that coordinate system. You have to decide where 0 is, and this problem tells you where 0 is. Where are we finding the center of mass with respect to? Where's our origin? Center of the Earth. This is very important because if you do not know where your 0, 0 is, and you tell someone it's located at 5 meters, from where? From where? If you don't set a reference, if you don't set an origin, no one's going to know where that's located. If I tell someone that thing is 5 meters away, from what? You got to have a reference. This is my origin in this problem. It tells you, I will tell you the origin in every single problem. Otherwise, every single one of you can get a different answer. I will tell you where the origin is in every single problem for center of mass. Okay? So, now we set up the equation that looks gross, and I'm going to show you all it's not that bad. Center of mass equation is, so our center of mass is 1 over all the masses added together, times the sum of each mass times where it's located. And this is where I'm going to let you all try to build this equation for a second. I want you all to try it. I'm not expecting everyone to get it, but I do think a good amount of you can figure this out. And I will, of course, show you all. Try to build this equation, y'all. It's almost like sight reading music, but now it's sight reading math. Can you sight read a math equation and determine what the heck it's saying? So I'll probably just do leave it. I don't want Yeah, good. Yep, you just sum up the masses on the bottom. Yep. Yeah. Yeah, and if you have the sum, yeah. And if you already have that sum sign there, or like if you are summing it, you can get rid of that sum. Yeah, that's exact. That is 100% what it's doing. Now the question is, how far away is the center of the Earth from the origin?
But this doesn't use the center of mass.
So this R is how far away the center of Earth is from the origin. So for now, we're just kind of building it with variables. We're going to start plugging in things at some point. But try it out. Can you side read this equation? You are going to see so many equations in your life, and when you all get into a job one day, you might not have someone to explain that equation for you. Can you read math? Like musicians need to be able to sight read music. Can you sight read math? Because you're going to see a lot of gross equations in your life. Can you understand them without someone explaining it to you every time? Yeah, you just gotta put what you're. You just gotta. Yeah, you get rid of. You will sum whatever it tells you to sum. Yeah. That just represents how many. So in this case, how many objects do I have? Yep. Yep. N is the number of objects. It's just an index. Yeah. Yeah. How many objects do we have here? So you just have 2 objects and something together. Yep. Yeah, it's to represent the general expression for that is to represent. Because I could have 1 million objects, in which case I would add 1 million terms. All right, y'all. So let's do it. Let's build this equation, and I probably don't have enough space here. Okay, so we just sight read this. We're going to sight read this equation. So R center mass equals, and just like you sight read music, 1 note at a time. 1 over the sum of the masses literally means add the masses. Great. I've added the masses together. Times the sum, and this is where it gets each object times its mass of the object times where it's located. So I have the mass of the Earth times where it's located, plus the mass of the moon times where it's located. And that's the equation. We built it. Now we look at this equation and we ask ourselves, do we have all these variables? Because we need to be very, very careful here, because I can assume that half of us, if not more, are going to plug in a number in the wrong spot. And you're going to see what I mean. The mass of the Earth. Yep, we got that. That's right here. I'm going to use a different color for the mass of the moon. We got that. That's kosher. That's going to go there. We have the radius, how far away the moon is. We have where the moon is located with respect to the origin. We don't have where the Earth is with respect to the origin in our list. Those are not the same R's. Capital R is the radius of the Earth. This R, this lowercase r is distance from origin to center of Earth. And I totally don't have the room for that. R is not the radius. R is not the radius. R is how far you are from the origin. Y'all tell me how far is the Earth, the center of the Earth from the origin? The distance from the Earth to the origin is 0. It's very subtle. And that's where I want to remind you all. These R's are not radius. They're not radius. They're where you're located. They're where you're located. So now you can do the math.
What did you say? Sorry.
Uppercase. It's 4 million meters away from the center of the Earth, which is a pretty big distance. Now, relative to how far the moon is away, it's not that big. It's 1/100th of that. But the Earth is actually, the Earth itself is actually orbiting a spot inside itself, which is a weird idea, but that is the reality. The Earth itself is orbiting that spot.
I got a minimum for B and I was confused. And then just looking at the answer and the radius.
Yep. So try it out, y'all. Plug in the numbers. Everything you need is now up here. Again, I will do it as well, but I want you all to try it for yourself. The center mass of the Earth is like here. The Earth is not orbiting. The Earth is actually orbiting a spot that's not its center. It's weird. So just to plug in the numbers, our center mass is 1 over 5.97 times 10 to the 24 plus 7.36 times 10 to the 22 times 0 plus 7.36 times 10 to the 22 times how far away the moon is, 3.85 times 10 to the 8. And you just plug all that stuff in, and you all find that the center of mass of the Earth is pretty far from the center of the Earth. It's 4 million meters from the center of the Earth. So, and that's where the Earth is actually orbiting relative to the moon. They are both orbiting around that spot. Yeah, we get close enough. 4.69 times 10 to the 6. A very extreme example of this is a binary star system. Binary star system is a system with 2 stars, and they orbit the center mass of the 2 stars. So, you take this to the extreme. The Earth is much bigger than the moon, but what if you have 2 objects that are somewhat similar in size? It's not that one object orbits around the other; they both orbit around a shared center of mass, which is cool. So, and if you have a 3-body problem, it's too complex and you can't solve it easily. So, all right. Part B, you just subtract the radius of the Earth from that. So part B, where is it located with respect to the surface of the Earth? 1.73 times 10 to the 6 inside. Inside the surface of the Earth. I'll put a negative in front. From. All right, so see if you can get the second part. This problem looks gross, but it's a center mass between 2 objects. They just have to be big objects. All right, we will do one more problem and be done. We're going to do one more problem and we'll call it good for today. Okay?
Oh, yeah. Okay, that makes sense. Because the moon is like 3.5 times more expensive than the Earth is on the sun, I think.
Yeah.
So it's actually like pretty variable. Alright, Earthly distance is 384.
Yeah, it's a classic, right? Yeah. It's classic.
If you do it there,
Yeah.
that's better, but I want to get like an actual meter system.
Oh.
Yeah. No, part B is gonna be awful. We got 1.68. Ezra, did you get negative 1.68?
Because we used the 3.85.
Yeah, I didn't like the framing they did this problem is the distance they gave. The way they wanted you to do this problem was the radius of the Earth, and then you would add the distance, but I didn't like it. So, all right. So we're gonna do a two-dimensional problem, which is the same thing you all just did, but now do it twice. I have a very exciting thing to tell you all. You don't actually have to convert the mass in this problem because the units all cancel out. You can convert mass to kilograms, but if you leave it all in terms of grams, it actually all cancels out. Either way, 3-point masses are placed at the corners of a triangle, as shown in the figure. Also, fun fact, same thing. You can keep it all in centimeters if you want as well. You don't have to convert any units for center mass. Okay, the final answer will spit out centimeters if you leave it in centimeters, but that's fine. Center mass, you don't need to convert units. Just recognize that your final answer will be whatever distance units use. Find the center mass of this system using the location of the 150-gram object as the origin. Remember, I will always tell you where the origin is, otherwise there's an infinite number of answers. So this is my origin. This is my 0, 0. And I want to remind you all something very, very important before we start any math. If I'm to the left of the origin, is it negative or positive? Direction matters. Otherwise, you'll get things on the wrong side. Try it out. Write down your givens. X and Y's, all that jazz. Split things into X and Y. Split. You can do this. Are y'all doing this? I'll put the answer up here. Yeah, center mass is one of those things I haven't done like. So yeah, I opted to do this instead of harmonic motion because I felt this was more useful for them. If they were all physics majors, I would opt for harmonic motion. Whether or not you all do this correctly is I'm just going to look at your givens. If your givens aren't good, the rest of the problem is going to go south. If your givens are good, this problem's easy. That's all I have to look at to see if you're doing it right. You need to split things out. So you have your R. I want to see X, the X location of object 1. I want to see the Y location of object 1. I want to see the X location of object 2. I want to see the Y location of object 2. I want to see the X location of object 3. I want to see the Y location of object 3. So in the center mass equation, it uses R. R is where you're located. So we're going to split X and Y. So you're going to set up 1 where it's like 0, 1, the X. Yeah, you get to decide which object's which, but yes, one of the objects is X position and it's Y position. Which is nice. Generally, we like to pick the origin in a place where you don't have to worry about one of the objects. How goes your initials?
Nice. So what are you trying to find? Oh, this is the X center mass. Is that what you're calculating here? Write down your givens. So your givens are going to be where are they located? What's the x coordinate of this object? What's the x coordinate of that object? What's the y coordinate of that object? What's the x coordinate of that object?
So to give you all some guidance on the givens. All right, first we're going to label which object's which. I don't want to write 100 kilogram, 500. I'm going to call this one 1, this one 2, this one 3. Make a nice table with the X and Y locations of every single object. This is where I said I'm looking at step 1. Where are they located? Where are they located in the X and in the Y? And then try from there. And you're going to do center mass in the X, and you're going to do center mass in the Y.
I assume you use the same definition I did. You can totally do that. You called X up and down and Y left and right, which is fine. That's, you just have to realize the Y is so deal.
Which is fine. Your answers will just, your final answers will be flipped. And that's all I'm like. So you could just, I recommend probably fixing it here because when you look at this in the future, you're going to be very confused. Alright. And I'll be honest, y'all, this is the last problem we're working on, so if you achieve success, if you don't have any more questions for me, you're good to go. I mean, like, that's always true in class. I don't have your minutes or anything like that. I don't keep tabs on who's still here. But I will work through this problem, but if you get the right answer, you don't need, like, you can stick around or leave or whatever. I'm not going to do anything after this except I'm going to work through this problem in its entirety. But if you got the answer, you probably don't need me. But I will continue to work through this problem, so I'm just giving you all a heads up. If you solve this, you don't need me anymore for the rest of the class.
Okay. All right. So dx is ax is 0. Good. Y goes
All right. So, just to kind of put the numbers here, object 1 is at -4 centimeters. Object 2 is at +3 centimeters, 0, 0, 0, 0. Mass of 1 equals 100 grams. Mass of 2 equals 75 grams. Mass of 3 equals 150 grams. We're solving for the X center mass and the Y center mass. Step 3, how do you do this? So that's the expression I gave you all. Just replace the R's with X's. So the x center mass is the sum of masses times the square root, or not the square root, the sum of mx. The y center mass is 1 over the sum of masses. You got it, and then you just plug in you sum them up just like we did the last one. And yeah, so I'll leave that here, and then I will do the last step as well.
Oh, I see what. Okay.
So then build the equations like we did the last one.
It's simple. Oh, sure.
I was gonna tighten my sash.
Someone else.
Time to go home and practice.
Okay, right.
How lucky are you? They're just going to a 9 to 5.
Actually, five. Okay.
Nice.
Whatever you describe.
I get it, bro. I get it, big bro.
But it's up to you. I just put the answers to that. I just totally put the R center mass equal. Parentheses x squared y.
And then
Generally, that would be nice. R center mass equals parentheses. It's a little bit more organized. Well, let me rephrase it. It's a little bit more succinct. To do that R equals parentheses. So that's generally why we write things that way. But this, that
I guess
represents.
because I'm like 2 meters.
I would.
yeah.
That's how
How we doing?
I guess it looks hard when standing up.
Yeah. That's great. Yeah, and why is there only one term here?
theater thing.
Yeah.
And
Zero.
Any
Any questions?
I was like, I'm exactly. I'm laid down around. And then like,
No one needs me.
5 bars.
Sure.
5 bars, 5 seconds.
Nope. No, everyone that's teaching is I think they've been assigned.
All men are friends.
Very much.
yeah. But it makes sense, like the.
Yeah, that's fine with it.
I was almost.
Bro, be right.
Let me just turn off
Yeah,
the stream.
come on.
Nice.
It was like 6.67.